Okay, so just checking that I'm getting volume. I am not getting volume. Okay, yep, good. I'm getting volume. It's kind of important for recording. So welcome to Advanced Data Science. So this is I don't know why, we still can't work out why we only start halfway through the term. We'd like to start at the beginning of the term. We'll try and fix that next year, but quite an intense short course as a unit to sort of set the context of the emerging domain of data science and guide you through the data science pipeline. So this is the second year we're running. If you haven't found the course webpage, it should be linked from various places. We have, everything is publicly online. Let me get the URL. So that's ml@cl.github.io adverdus. Last year, it was just ADS. Can you tell why that caused a problem? It got ad blocked because it was ads. I think it took me ages to work out why it wasn't working on some machines, because it was like ads. So that's why it's ads this year. And hopefully you won't find broken links pointing to ads. But if you do, you'll know what's going on. I couldn't work it out by the start of the lecture. There's someone in the lecture class that pointed out why it was only working on some girls. Well, look, my garage door is open. Yeah, so what we're going to do is we've got a set of lectures and then a set of practical sections. So the practical sessions make up some percentage of your mark, and there are check sessions for those. So all the details of the practical sessions are here, so you can go and have a look at them in advance. Just be a bit wary that we have a tendency to update and fix things on the run into the day. So if you do start it early, you might find some aspect of it broken. Or you might find there's something that we change on the day, but it just gives you a sort of sense, because it's quite a compressed course of everything that's to come. So alongside the practical sessions, there's some review things that it's entirely up to you as to whether you do. You can have a look at the practical and see if you want to do the review, but so that's sort of launched from today. That should be working today. The review session that's just on probability and a few other things that we're going to eventually make use of. And there's a second review, which is, I mean, Carl's practical covers much the same stuff. That's just my similar material to the material that Carl provides. So the actual practicals that we have check sessions on is practical 1, practical 2, and practical 3. And yes, if you go through, what you should see, he hopes, is that when you click on that, first of all, you'll get the sort of overview as HTML of what's in the practical session. But the real thing to do is that most of our work, we tend to do it in Colab. So we'll look at that. So that's Colab notebook. Now I did have cats on there. I actually prefer dogs, so I switched it to corgis and crabs. But I don't know why they have crabs. But look, it's clearly approaching Halloween. So the corgis have got pumpkin heads. So this is the Google Colab. Have people here not used Colab before or don't know what Colab is? The Colab is a Google hosted version of the Jupyter Notebook. The Jupyter Notebook is a way of doing something that is a bit like literate programming, so integrating text and code. Now, what I suggest you do when you do any of these sessions is, first of all, expand sections. I have no idea why Google Colab decides to collapse things, because everything in here is designed to be seen by you. The collapsing button is that one, right? So you can collapse sections yourself. And I mean, this would all run just directly on Google. And the reason of using Colab, you can do it on your own machine. The reason for using Colab is because it just gives us a uniform interface where we know that the installs we're suggesting are working. So for example, this lab is installing some utilities first. I can test it on Colab, and I know that you've got an environment that's effectively exactly the same. You won't have to worry about installing various things. So you'll see almost all our labs have to start with some installed. This one is then downloading some data at the start. So I'll just say yes to download that. But then it just sort of goes through doing some plotting and whatever else. That's the review and refresher one. It's all on sort of conditional probabilities and stuff. You may well feel you don't need to do that, and that's fine. Any questions on that? Yeah. So basically what will happen is when it comes to the practical sessions, you'll get checked on, you're going through the labs and sort of showing us that you've managed to complete the contents. So that's the sort of practical and review. And so if it's got as practical, it's going to be checked. If it's review and refresher, it's just for your own interest. Yeah. I'll pause again and say any questions. I know, like, undergraduates in Cambridge have been trained not to ask questions. I hate that. So I'm going to try and train you to ask questions. I know you're not all undergraduates in Cambridge, but for example, in our master's course, we tend to get quite a lot of questions. Okay, so lectures. So alongside that, you'll see that we've got the set of lectures going through. Now, if you go into the lecture itself, you'll see each lecture. In my case, Carl-Henrik does it slightly differently. He'll provide PDFs, but we provide on these pages is either the links to the PDFs, and I'm also providing notes here for you to go through and sort of review what's in the lecture. What you'll also see is you have a YouTube video, and that YouTube video is last year's version of this lecture. At the end of this lecture, I'm recording now, so look, you can see me last year doing that, standing in the same position on the corner there. At the end of this lecture, I'll update and put this year's version of the lecture. But if you go onto that channel, you'll be able to find last year's version of the lecture, and you can choose which year you watch. Hopefully I say roughly the same thing. Hopefully Carl-Henrik says roughly the same thing. Sometimes we might choose not to update the video just because we think we didn't do a great job this year or whatever, but you're not, or sometimes we might even make an error. We've also allowed, Panopto should be recording this. I kind of prefer the YouTube thing because I had an experience. I've always recorded my lectures in Sheffield, and once I relied on the recording system, and they have things like auto delete that kills. So I have lectures that are missing because I relied on the lecture recording system. I'd rather put them on YouTube. Maybe that will auto delete them at some point, but that will be a bigger international crisis rather than a personal crisis of loss of lectures. So I'll switch to the slides. My slides are in Reveal, so they're sort of HTML. Apologies if you're used to sort of using PDF slides. You find there's various things you can talk about, and I'll do a little rant. One of those things could be PDFs. I don't understand why our electronic format is targeted at printing. We should have electronic formats that are targeted at reading on machines. They have their uses, but I prefer to sort of try and use HTML, which has its own limitations. So without any more ado, I can start the course, but you can ask a question. Questions? Go ahead.
We have 6 practical sessions, so and we have 5 practicals.
You've only got 3 practicals, really. Yeah. So you'll see on each one, I think, it should say like when you're going to be checked. So some of them are check sessions, and some of them are also the 4th check is actually a part of the assignment. So good question. So the assignment for the course, which is already online, but again, we're going to have to probably do a little bit of updates for reasons I can explain in a moment. The assignment for the course is set now so that you can see what you're going to have to do at the end. But the 4th practical check, so there's 4 checks. And the 4th practical check is getting you to use the machine learning system you've built to make a prediction in the lab. So we're using lab classes for things beyond. So we set the practicals on certain weeks, but then we're checking the practicals on other weeks. And then there's one final session that is just before your assignment submission. You'll see it sort of pushed out a little bit from the other sessions. And that's where we get you to live make predictions with the data science system you built for your assignment. Yeah, makes sense. So I think I've got it on the course overview. So this is Carl-Henrik and me. And he doesn't really take his photo like that. It's just my automatic system for circling. His photo was slightly too big, and I kind of quite like the way that he looks like he's poking up at the circle like that. So So why I think this is a really interesting course to teach is because data science is an emerging field. And one of the things I say is I've never seen data science done well. I don't think anyone knows how to do data science. I think we hear a lot of talk about it, but I don't think people know how to do it. But I have seen places where it's done better. And so one of the things we're going to try and teach is some techniques for how to try and do data science better. I mean, if you think about where we are with data science, which in some sense is a version of computing where instead of programming, we're trying to get data to do the decisions, and therefore we're programming the computer to assimilate data. And how long that data has been available, you have to sort of take us back to say something like the 1990s to understand where we are. Like, so think of the 1990s, what was their understanding of large system software engineering? It was pretty poor. They wrote a lot of, well, more of the sort of 90s to the early noughties. Funnily enough, when I started my lectureship, I used to teach a bit of software engineering for some reason. And I used to work with a guy called Stan Price, who just knew about all the software engineering disasters. And we're right in that zone of data science disasters at the moment. And you can see that with Facebook and Cambridge Analytica and all these other things. It's just really shocking practices that probably shouldn't be shocking when you think that these are very large scale complex systems and people just don't understand how to deploy them. The weird thing is they do have an understanding of how to deploy computer systems. So what you've got this weird combination is these things are being deployed at enormous scale without an understanding of what the potential pitfalls are. So that's why it's a really interesting course to teach. It's a great privilege to teach you because you are going to be the sort of leaders who go out into industry and fix this. It's going to be something you get to do in your careers if you choose to continue doing data science. So what we chose to do with this course is I start the first sort of set of lectures where I'm just trying to set that context. And a lot of it is kind of pretty non-technical. The practical sessions will have technical things in. So the practical sessions will be trying to sort of give you a sense of what the real world job of a data scientist looks like. So there is elements to that, but as Carl-Henrik will tell you when he teaches a bit of the machine learning side. We're both machine learning experts, by the way. We can stand here and make you do difficult derivations if you want, but that's not actually the problems of data science in the real world. The fact that we managed to make these models work is what causes the problem. So what we now need to do is think about how we fix the problems. So the first of a set of lectures are really going to set the context of why this is a difficult thing to do outside the sort of mathematical side. And then there's a lecture where I sort of will try and give you a framework to think about how you approach a data science project. It's not a rigid framework, it's what I'd call quite a loose framework. And that framework is what we're going to encourage you to use when you do your assignment. And your assignment will be a sort of practical example of the thing you might be asked to do as a data scientist in the real world. So that is the sort of first session of week 5, a data science process. So it's the 4th lecture, because this week 4, I'm just going to complain how nothing works, right? So first session of week 5, then I'll sort of give you a sort of process where we think, that gives you the inkling of how to try and structure your thinking around how you approach data science project. Now, for those of you who are doing, one reason for setting things up like that was because many of you may be doing data science projects as part of your part 2 projects, if you are on the undergrad. And when you look at the pink book, it says various things around you should explain your practices and how you're addressing what your formalism for approaching the artifact you're constructing as part of your project, right? That turns out to be pretty easy to do if you are building a piece of software, because there's a bunch of established practices around that. If you're doing a data science project, one of the analogies I'll use in the course is data science isn't like programming, it's like debugging, right? Because it's like being given a sort of data set, which is like a piece of crap code that you didn't write, and having to make API calls on that data set, right? So how would you do that? You would have to debug that crap code a lot. And so the sort of process you tend to go through in data science is much closer to debugging than it is to programming. When I had that realization some years ago back in Sheffield, when I was doing data science projects with computer scientists who were only trained in computer science, because at the time, machine learning wasn't cool. So they didn't have much machine learning training at all. And that was an analogy I used to help them think about their data science project. I thought, oh, this is great. So I just have to look up the processes for debugging, right? What are the processes for debugging? They are, don't write code with bugs. Debugging is hard, and there aren't really very formalized processes for it. There's just a lot of things around testing and controlling how you write your code and detecting bugs as they occur to prevent the existence of bugs, because it's really, really hard. But in some sense, that's the process of data science. So we'll give you a data science process, which is kind of loose. And, you know, that I'm sure there's flaws in it that you can use for your project. And the idea is to help you use that to build a narrative for the project for this course, but potentially, you know, if feel free to use it in your part 2 projects as well. Yeah. Carl Henrik's then going to sort of bring in a set of models that we suggest you use for the assignment. So a lot of the assignment you'll see is going to be more about justifying, setting up your access to the data set you're going to use and justifying the features you decide to include. So you're going to be given, basically we set you up to do a house price prediction problem. And, you know, you can, where the first session is about working out how to get UK house price database onto an AWS RDS service. So you've got it as a database service. And then the second practical session is about teaching you about like OpenStreetMap access, so that you can decide what features you might like to use into making house price prediction. And then the next thing is about, well, what sort of modeling can I do to try and pull these things together? So those are the 3 stages you'll find out about in the process we have, which is called access, assess, address. So the access is get hold of the data, assess is like work out what's in the data, and the address is address the question, make the house price prediction. And so that maps quite closely onto the practicals as we do them. So those, and then we sort of have a couple of mop-up lectures on the end. And then that's the key thing here, project results check. So one of those practical sessions is where we actually get you to make predictions live, right? So what we're going to do is you'll make a house price prediction system through the assignment, and we're going to lead you through the stages in the practicals about how to do that. And then what we'll do is we'll stand in front of you and say, tell us how much it would cost to buy a detached house, and we'll give you a latitude, longitude, and then your systems will make predictions. Now, we will not be scoring you on the accuracy so much of the predictions. We just want you to get at an early stage, like what your pipeline finished and completed, so that you then finish the thing that we care more about, which is your write-up, your justification about why you chose those features and how you chose to pull those things together. Okay, so that practical session comes before the assignment deadline, but it's trying to force you, because you'll be required to do that sort of live. So you'll be trying to, you know, it's the equivalent of someone's clicked your web page and wants this prediction. Okay, so as I say, the assessment already available in Moodle. There's a couple of updates to that might well happen. The main problem we had on this course last year, which was the first year of running, is things we were led to believe around AWS accounts weren't true. So basically what we wanted to happen is you should all, like in the ideal world, you would all have AWS accounts associated with your CRS ID at cam.ac.uk. And we were told that this was true, and we were told that you didn't have to provide credit card details to fire up those accounts. That turned out to be not true, and was quite a problem, because you'll see the first lab session is teaching you how to sort of use that account to set up a database on AWS. And then the idea was that you were going to use that database service for the whole rest of the lab. It's really difficult to find a cloud service that doesn't require you to give a credit card number. Even that so obviously makes it extremely difficult to teach that cloud service. And we're sort of at the point where we think it would be good if you want to get the exercise in the assignment. I think it's a great exercise to go through just to set up something on the cloud. But I think where we're probably at with it is once you've done that, we'll then give you RDS setups that we've set up to use on our AWS account. So you are using AWS to do this. The reason we kind of have to do that, we found some free cloud services that apparently did everything we wanted to do, but I think that our data set size in terms of all UK house prices is like 3.8 gigabytes. And we're interested in getting you to work with data sets of that size and scale, because that's the type of thing you face in the real world, and it changes how you make predictions. But we couldn't find a free service that allowed us to run the whole pipeline of this lab and allowed you to operate with a 3.8 gigabyte. So you get all the way through and you thought, oh, they limit the amount of data we can upload, or they limit this, or they limit that. So in order to emulate the process of things, if you do have AWS accounts that you're perhaps like, because you have your AI for ER and you've got that set up already, I don't know, then we'll freely let you use them. But I think at one point you're going to get a request from us fairly soon to provide your CRS IDs, and we're going to set up usernames and give you account names through some process so that you can run that. But you'll see in the first lab, we would like you to go through the process of seeing what we've had to do in order to set that up, because we have to do that for you individually. Okay. So one of the things that you should be able to do is complete the assessment as we teach. So because what we're setting up is teaching you each component of the assessment. So you're sort of thinking, oh, I'm having to do all this work on the lab classes, but you see it closely mirrors work that you're going to have to do in the assessment. So what we encourage you to do is, after each lab session is complete, progress your assessment, because you'll get feedback in the lab session that you'll be able to integrate in the construction of your assessment. And then what we'll also sort of hope that you'll do, expect you to do is, yes, data science, also like debugging or any other process, you're going to go through it in a certain way with certain beliefs about how things should come out, and you'll find that isn't how it works, and then you'll find actually you need to refactor your structured approach to that, right? So that will involve revisiting your questions at some point as the deadline approaches to refactor your code. Now, what do I mean by that? Well, the artifact you'll be giving will be in two parts. One will be a Python library that is doing most of the uninteresting access stuff you need to do, and the other will be a Jupyter notebook that tells the story of how and why you were making the assessment in that way. And part of the refactoring is deciding what should be in the notebook and what should be in the library, right? So the library should be, in effect, it's like telling the story of how you went around the debugging. So some future data scientist who sees your process can look at your process and say, oh yeah, I get why they've done that now, right? Rather than having to go through the same process and realize why you made those decisions. Or they might look at it and say, oh, it doesn't look like they thought about this other important thing. I'm going to try this other important thing. So that's what the artifacts we want you to create are. You're moving forward. You provide a Python library, and ideally, like whoever the future data scientist who looks at your work would be like, oh, great. And there's already a Python library that I can use to do a bunch of the stuff I need to do, right? Because you've sort of developed that as part of the process. And that's what we call the sort of, the way of doing that is what we call the finesse framework, the access, assess, address framework. Okay, I'll stop there again, see if there are any questions at that point, because that was all about the sort of the philosophy of the course. And I don't know, there's probably not a, because we made it up, maybe there's a course which has the same type of philosophy, but yeah, I don't think there is. So if that's like surprising, there may be questions. I'll pause again, questions around that. No? Yes? So the trick is, because we were given this compressed thing, we said, okay, well, we'll give them room to do assignment while you're doing your labs. The idea is to educate you as we progress. Yeah? Okay. Great. And at the check sessions, you'll also have the chance to sort of, we'll bring in some of our wider team people, so you can also sort of ask detailed questions about how you might do various bits, because there's going to be very little technical in what I say in the lectures, right? But the idea is that you find out the technical stuff through the notes in the labs. Okay, so let's start on the sort of motivation of why this is difficult. So who said this? There are three types of lies: damn lies, and statistics. Israeli. It's good, actually. It's very impressive. Yeah, Disraeli. Who was? People know who Disraeli was? Yeah, he was the prime minister sort of in the 19th century. So it's actually accredited to Benjamin Disraeli. It's accredited to Benjamin Disraeli by Mark Twain. In Mark Twain's biography, he sort of says, Benjamin Disraeli said, there are three types of lies: lies, damn lies, and statistics. Of course, Churchill wasn't alive then, so people couldn't misattribute quotes to Churchill. So my theory is that before people misattribute quotes to Churchill, they misattributed them to Disraeli. But I think Mark Twain was writing in about 1904 in his autobiography. And Benjamin Disraeli did die in 1881, so he couldn't complain about this. But what's interesting about this is look at the period that we're talking about statistics from. So Disraeli was a statesman during, I suppose, the height of empire in Britain. And one of the things that was emerging was the science of how you operate a state. How do you operate such a large organization? And in some sense, not just Disraeli, but that approach, the thing we have now, was kind of invented across this period. Now, statistics is interesting because when we look at statistics in that era, what the claim is, it's being used to manipulate. Now, this is my modern update of this quote. There are three types of lies: lies, damn lies, and big data. And the reason why I think that is apt is because we're facing a very similar situation to the situation Disraeli and other people faced in the 19th century with the statistics they were given. But we're just facing it at a different scale. And we can even see the history of how it was addressed. Does anyone know who this is? Karl Pearson. So he died in 1936. He's a very controversial character today because he's involved in the early statistics movement, and the early statistics movement is closely interconnected with eugenics. So but he was at UCL, and he founded the first statistics department. His mentor was Francis Galton, who again is closely associated with eugenics. But when they weren't sort of misapplying the results of statistics, one of the things that this community did was spend a lot of time thinking about what it means to collect data and draw conclusions from it. Now, the important thing is, that's what you might think of today. If you're being taught statistics, you'll get taught p-values and all sorts. But that's this community: Pearson, Fisher, Nyman, these sort of people that existed, had their careers. He died in 1936. So these people had their careers around the time that Mark Twain is writing. And a lot of the work that they were doing was trying to understand when it's valid to draw conclusions from data. What's like the main technique we have for that? Anyone? Main technique. Significance, yeah, but how do we get significance? What do we have to do? It's true, we have significance testing, but what underpins significance testing, something that you hear all the time when you're trying to design an experiment that you should try and do. Hypotheses, yes. So you design the experiment often with a hypothesis in mind, but there's, like if we do a drug, if we want to test a drug and we've got controls, yeah, and how do we control? What's the typical technique? Yeah, but what do we have to do to the data? There's a sort of a specific thing. Randomization. Randomization is like the most important technique we have. Yeah, so if I want to sort of understand how COVID is distributed across the country, and so that's surveillance, it's expensive to get that data correctly because I have to ensure I sample the population randomly. And many of the failings we've had in data analysis in recent years are to do with the challenges of properly randomizing and using proxies for randomizing, whether that is polls or whether that is development of drugs for particular strata in population. So this group, the reason randomization is so useful is it turns confounding information into noise if you correctly randomize. And that's the sort of thing, that's the technique that this group developed. So we don't release drugs until we've done trials. And those trials involve treatment and control, randomization in populations. And they have to deal with confounding effects, you know, which are, the randomization is there because if you don't do it, the confounding effect can appear in the treatment or the control and then undermine your conclusions. And these conclusions can only ever be made probabilistically, right? They're only made with a sort of confidence, which we get from significance tests and whatever. So there's a sort of serious question. What's happening is that people are sort of, oh, well, there we've got all this data. What are we going to do with this data? This data is virtually never randomized, right? So now we're trying to draw conclusions from this data without the benefit of randomization. Yeah. So that's why we sort of have such significant problems. Interestingly, people know about A/B testing. So one of the really difficult things, so A/B testing, there were a few nods. A/B testing is a randomized test on a modification, for example, of an interface of a website that I can find extremely confidently that my users prefer this form. So the sort of thing that Facebook find out through A/B testing is that people like posts with a picture on them, right? So they tend to move up posts which have pictures on them. You know, you find out what clickbait works through A/B testing, right? The depressing thing about that is you don't know why. You can find that out at scale. You can find out what people are attracted to at scale. You have no notion of whether it's good for them or why they are attracted to those things. And what you have now is interfaces on your phone and everywhere that are just highly optimized by really good, large quality statistical trials. Unfortunately, they're not necessarily being optimized in your interest because they're optimized for your engagement. Now, there's a really interesting thing that I think underpins the challenges we face, and I refer to it as embodiment factors. So I think the real challenge we face is related to the ratio between our ability to compute as humans and our ability to communicate, the bandwidth over which we're communicating. So if I look at how rapidly I can communicate, if I'm just talking to you in sort of, I probably speak slightly too fast, habitually I do, I need to slow up more, but if I were to talk to you, trying to teach you about data science in a sort of reasonable way, then the amount of information in terms of Shannon information that I'm communicating to you is about 2,000 bits per minute, right? So that's the communication, spoken communication rate. So the one that is effectively bidirectional. Of course, we absorb information visually. The best estimates I've seen for your optic nerve, which isn't a nerve, by the way, it's a projection of the brain, is that it's transferring information at about 1 megabit per second, right? That's actually way lower than any camera chip on your phone. But that's not bidirectional. I can't send information backwards. I can by waving, but not through I can indirectly send electromagnetic radiation to you. Look at me pushing it back to you, but I can't do it at the rate at which I can absorb it. Yeah. So there's definitely information in my expressions and these sort of things, but the main sort of information I'm talking about here is vocal communication. Now, if you sort of try and work out how our computation, our ability to compute, it's quite hard to estimate, as you can imagine. So I spent a bit of time poking around what estimates are to simulate a human brain. And the best estimates I could come up with that you could probably just about simulate a human brain on the UK Met Office's supercomputer that sits in Exeter and spends its mornings computing our weather on, I think now 1.5 kilometer cell sizes. And it spends its afternoons running climate simulations, right? And that machine, as far as these estimates, whatever the validity of these estimates, would be capable of simulating a human brain if we knew how the human brain was wired together, which we don't. But roughly speaking, that's true, right? So that's quite a lot faster than the typical machines. Maybe these slides are getting out of date. So that machine does about a billion calculations per second, whereas a typical machine is 100 billion. Maybe that's larger now. I don't know. But you can see it. These things are, we are faster to compute and slower to communicate. Because if we look at how fast a computer can communicate, then if it's using gigabit Ethernet, then that's 60 billion bits per minute. So let's just sort of pause and consider that number, 60 billion bits per minute. So imagine these are salaries. So imagine that you're graduating and I'm offering you $2,000 a month. And you think, okay, that's not great for my salary. I mean, but a lot of people live on a salary that large. but it's kind of low today. Imagine you're graduating and I offer you a salary of $60 billion a month, right? That gives you a sense of how dramatically different the machine is in its communication capabilities to us. That's up with how much, I think it's roughly the budget of the UK's health service and social services combined, 60 billion a month. It's a sort of like you could wipe out all, they keep talking about 37 billion missing in our, that's what they're trying to find through tax savings. So that's like 1 month's worth of this salary would save that. So these things are operating at different scales. And the way I like to try and summarize that is, imagine, we can't do this and computers can't do this, but imagine a computer could access every computation it's done in 1 second and share that computation with another machine. Well, in order to do that, it would take, if it was computing at full pelt, it would take about 20 minutes to share 1 second's worth of computation, right? Imagine a human could access all the neuron firings and everything else that's underpinning us, and then tell them to another human. It would take that human 5 billion years to tell the other human 1 second's worth of computation. So the sort of point about that is our intelligence is highly locked in. So you can look at people who are actually, there's a guy, Jean-Dominique Bauby, who was a Frenchman who lost his brainstem. He lost the ability to move apart from his left eye. His right eye had to be sealed because for medical reasons, so he could only wink with his left eye. Bauby could transmit at about 6 bits per minute. They should have had a better coding scheme, but he wrote an entire book, and we can find out that he communicated around 6 bits a minute. So that's $6 a month, right? Not very fast. It's about half a word per minute was what he was communicating with on average, because the estimates I'm using are 12 bits a word, which is an estimate from Shannon, actually. But $6 per month is far closer to $2,000 a month than it is to the machine. So we are far closer to someone who's locked in winking than we are to the machine. Another way of thinking about this that I was playing with recently, and I think that this is roughly right. Me having this conversation, well, if we were to have a two-way conversation, the amount of information that would exchange between us is approximately the same as the amount of information that is exchanging genetically across all humans at the moment. So how much is pushing down to the next generation? Just us having a conversation, okay? So that's across all 7 billion or however many billion people we are on the planet. Roughly the same amount of information passes if I'm talking to you as is passing across those generations, right? Us looking at that information transfer is the same as the computers looking at us talking. So the computers looking at us sharing information is like us watching the world evolve. Yeah? That's how different these things are. And that is so important in understanding why we have so many problems. Because the speed, it's like, there's this thing, it's like humans running around the planet are equivalent to the computers running around the planet, doing things that could be totally upsetting the processes of our communication, right? Okay, so sometimes I think about what does that mean for us? So I like to think of us having been highly cognitively powered. So if you think about our brains, I like old Formula One cars. This is a Lotus 19, which is the last generation before they started putting, these were highly dangerous. People died in these things, but it's got a really extraordinary engine. You can see the engine in the gearbox there. I did mechanical engineering. Carl Henrik did vehicle engineering. So we just secretly like to put cars up as an undergraduate. This is a V8 engine. So we're highly powered in terms of our cognitive engine, right? But if you think about our ability to deploy that power, this isn't even the right analogy. This is Marcel Renault in one of the earliest Formula One races. He died shortly after this photo was taken in a crash. But you have to think about a Formula One car with bicycle wheels. This is the closest image I could get. So think about an engine with all that power, but its ability to deploy that power on track is like narrow racing bicycle tires. Right? So basically, you've got this issue that you're trying to sort of explain to others what you think. And the way you're having to do that is really to control the way that you're deploying that power. That's how humans communicate. basically everything I've told you so far is to use analogies, right? And sort of say, oh, computers like this. They're not, of course, nothing like that. They're made of silicon. They live in boxes. They're nothing to do with that thing, right? But all this stuff means something to you because we sit within a broader context, a human context. And I can try and use your understanding of the human context. Some of you may or may not like Formula One. You try and use other analogies to try and get the message across in a small amount of bandwidth because we have a shared understanding of the world. And communication relies on that shared understanding, whereas a computer just communicates. It doesn't have a shared understanding of the world, but it can communicate much more rapidly. So the computer is sort of, it's set up in a very different way. It's lower powered in terms of engine, but it can deploy all that power on the track. So it's like while we're sort of dancing around going, oh, how do we move around this thing with these really narrow wheels and being really inefficient about how we share a communication, the computer can just whiz around us, right? And the fact that that's going on in the background and can be deployed at scale is where our problems start. So the way we sort of think about that context is in order to communicate with someone else, the first thing I have to do is I have to have a model of who they are. So I have a sort of model as populations, but I might have models of view of individuals. And before I say something, I have that model in mind and I choose carefully what I say, knowing what I think about the individual I'm communicating with. That person, in turn, might have a model of who I am, and they might even have a model of who I think they are in their heads, yeah? And actually, this sort of circular thinking does happen. There are psychological tests on it about how many levels you do that to, because obviously they could do an infinite regress, and we don't. We actually stop, I think, after about 2 or 3 levels, even at our biggest depth in terms of how much of this type of thinking we do. Now, some of this will be conscious, but most of this is totally unconscious, by the way. I mean, you can try and reason this, but most of you doing this is happening below your consciousness because you're not spending a lot of time thinking about this. It's sort of social intelligence, right? So that individual consumes that information, knowing who they think I am and who they think I think they are. So it's quite hard to say those things. And they just choose to say something in return, which is then assimilated on the other side. And then you get this sort of sideways conversation where we're slowly trying to get to the same place and have the same idea in our head. Now, when that works, I think it's really beautiful. And it's one of the most interesting things in life that most of the time when you're trying to work with other people, you're trying to indulge in this process. And there's very many ways of trying to get people to share ideas. But when it doesn't work, you end up swearing at each other. And one of the times you end up in the biggest arguments, I find, is actually when this slightly doesn't work. If this works, if this just fails, if you just don't understand what the other person's saying, you're just like, right, totally didn't get that. You don't have an argument about it. Where this tends to lead to arguments is if you're sort of 95% aligned, but 5% misaligned in your conversation. And then things really blow up in terms of arguments because you're 95% agreeing and 5% of you thinking, but that person doesn't understand the thing I understand, so they must be an idiot. And normally that arises from one of two things. Either, I mean, it often arises from different cultural backgrounds, but it often also arises from different objectives. So you see this a lot between arguments between machine learners and statisticians about things, because they're using a lot of the same maths and they know a lot of the same terms, right? So 95% of the stuff they're doing is the same, but actually machine learning and statisticians, as we'll mention in a moment, have fundamentally different objectives at the start. So it's like they're traveling the same roads because they're using the same maths, but their destination is different. So when they ask each other, why are you turning right here? You should be going left. Then they have a blazing argument about that. They've never stopped to say, are you going to St. Ives or are you going to St. Neots? They never ask that question. They just assume that they're all going to the same place, and they're normally not. And you get these big arguments. Now, there's this great sort of thing from Hyder and Simmel that talks about this, the Hyder and Simmel illusion. That is, this is right from the early days of animation. So 2 psychologists made this. I read the original paper, and it's just people writing what they thought when they watched this thing. Now, the interesting thing about this is you'll watch this and you will build a narrative around what's going on. Like very few of you will think that the large triangle is kind. You'll probably think that the small triangle is scared. And, you'll probably say the circle is hiding. There's a whole load of like very simple sort of, I think the most interesting piece about the paper is that they managed to get this video shown to a bunch of people in the 1940s, which must have been quite a lot of work. So the quality of the analysis is perhaps not what we might expect today, but it's a really early example where people are looking at the fact that this, in effect, you are communicating with someone from 1944. You know, you're like open mouth. How could they do that? And look, now they get rid of the chase. It's quite exciting, isn't it? But it's just triangles and circles, right? There's nothing, no people in there, right? But there is someone's imagined story in there that they're sharing with you, and they're using all those facilities, all that context to share that story. I have to move that quickly forward. That's quite good, isn't it? Sometimes, like, what will happen, you'll see everything I watch on YouTube. But fortunately here, you're just seeing lots of things about the Heidel symbol illusion. I mean, interestingly, so the evil YouTube algorithm's coming up with autism as a, because I think it's the sort of thing that, you know, if you are different places on the social spectrum, you will think different things about that video, and it's perhaps used as a test for that, but that's probably quite pop science, so we should be careful about that. This is another example. So this is a 6-word novel, right? So like all the quotes I use are apocryphal. So does anyone know who this 6-word novel is accredited to? Who do you accredit novels to when you're doing quotes? Hemingway, brilliant, yes. So if you want to say something about novels, you quote Hemingway as the person who, Hemingway never said this, but it is absolutely right that we should say Hemingway said it. So the ocean is, it's got a beginning, a middle, and an end. It's a 6-word novel. But the reason that that's possible is because this entire story is based on human existence and human context and what it might feel for that, and what the story would be behind that advert. So even though Hemingway didn't say this, but it's interesting again that whenever we come up with something like this, we insist some important figure said it, right? And it's easier to now check whether that's true or not because we've got the internet. But 50 years ago, it wasn't really possible to check that very quickly. So we would have just said Hemingway's 6-word novel. Now we have to say Hemingway's apocryphal 6-word novel. But the fact that we want to sort of accredit it with someone also says something about these things. Now, but when it comes to the computer, we might have a model of a computer in our head. We might communicate with the computer, and we try a few different things. The computer comes back, says, and then the computer says no. That's the sort of famous sort of thing. Computer says no. We don't have an understanding of how computers operate in the same way that we don't really have an understanding of how evolution operates. These things are at two opposite ends of the spectrum from us in terms of information transfer. Even you as computer scientists don't have a good intuitive understanding. What we tend to do with these objects is we anthropomorphize them. And that's a horrible and annoying word to say. So I just like saying anthrox because it's quicker. So we anthrox them, right? So we assume they're like machines. We do that with many complex objects. The reason we do that is because we're so used to communicating with other humans. It's the most complex thing we deal with every day. I mean, you're all incredibly complex, and yet I have an intuitive feel about you. Whether it's right, you're more complex than my feel, but I feel comfortable talking to you because I'm another human. I see you as simple, relatively speaking, because I have an understanding of humans. The computer, I try the same trick, but it just ends up being frustrating. So what does that mean for us? And I'll sort of end on this slide. Well, historically, this is the relationship we had with statistics, right? We have this new flow of information. So in the 19th century, people were starting to collect data about Manchester and saying, well, income levels in this area of Manchester are this level, and then in London, they're this level. Does that mean people are poor in Manchester, right? And then they were starting to anthropomorphize, anthrox data. And that's why you get lies, damn lies in statistics, because people are starting to overinterpret data. And in order to address that, they invented the field of classical statistics. Now, we are faced with this horror, that now there's a massive bandwidth connection between data and the computer, but we still have relatively narrow bandwidth interactions with the machine. As computer scientists, we're controlling this piece, right? And so this is an interloper in this relationship. Now, historically, that's classical statistics, and this is data science, right? Now, all the techniques of classical statistics are deployable, But the problem we've got is the potential for manipulation in this new route is enormous, whether that is purposeful manipulation or accidental. And in social media, I would argue most of it's accidental, right? It's foreseeable, but it's accidental, right? And that's what we're trying to deal with. And that's why no data science is yet being done well. And that's why I think this is an interesting subject to study. And most of it is just going to be, well, here's some things to worry about and some techniques to try and address those things to worry about while teaching you some technical stuff in the practicals. So we'll stop there, and I'm not sure when my next meeting is, but we'll try and pause outside in case there's any questions, because it's sort of important to be out of the lecture theatre, obviously, for the next person, in case there is one.